All right, so for those of you that are watching through the recording, I'm getting these tests through equitable access. So you should have access on Canvas. You click on equitable access on the left side, and you should have access to the materials and to these practice exams. Now, the way I usually do these is I ask you guys to pick questions that are beneficial to go over. I typically do this on a first come, first serve basis. So if I feel like they're questions that are very similar to each other, or I just already did that question before, I may opt to skip it so that way we can cover a higher variety of material. So great. So what questions do you guys have? Again, you can pick, and actually you can pick any of the exam ones here. There's a whole bunch. Um, Preferably start from the top, probably just top three, like 2024, 2023, 2022, but technically any of them. 20B, but which test? 2024? Thank you. Okay, great. 20B. 20 part B. So it says, I'm gonna get a whiteboard here. One sec. So it says, what is, and I should probably draw on that big pad and make writing easier, but it's fine. Um, what is the mass in grams of the excess reactant that remains? So the question says a common reaction in OChem is the oxidation of a secondary alcohol to form ketones using PCC. Oxidation of 15 grams of cyclohexanol react with 38.74 grams of pyridinium chlorochromate, or they give the molecular formula to produce cyclohexanone according to the equation below. So the first thing that you need to do for these limiting reactant problems, and the first thing that you should always think about doing, is converting all the reactants into moles, right? Because you have to see which one is going to be the limiting reactant, and the only way to do that is to convert to moles first. So if I go ahead, someone is unmuted right now. Thank you, because I can hear it echo. So we're going to convert these into moles first for both the cyclohexanol and the pyridinium chlorochromate, or the PCC. So this is for part B in particular, or I guess all the steps are going to be for part B, but you would need some of these for part A. You would need most of these steps in part A. So we take the 15 grams cyclohexanol. I'm just going to write it as CH. Um, I'll just write C6. I'll write the whole thing. C6H12O for cyclohexanol. We convert this into moles, just dividing by the molar mass. 100.16 grams of that per 1 mole. And then we're going to get some amount of moles. So let's see. Now, usually I do, yeah, let's do one more step here. So you can break this up into kind of different ways. Instead, I'm actually going to do something else here, which is, I think, more streamlined. So I'm going to do one more conversion here. So once I find the moles of the hexanol or cyclohexanol, I'm going to convert this into moles of reaction. Now, why do you do this? Because it makes it really easy and clear to see which one is the limiting reactant. So if you have two things and you find the moles of reaction that you can do, so just how many times you can do the reaction, right? Moles is just a counting number. So how many times can you do this reaction? The one that does the reaction less times is a limiting reactant, right? If I told you that 2 eggs and 1 cup of flour makes one piece of bread, and you have 3 eggs and 2 cups of flour. Which one is limiting? Well, per recipe, it's 2 eggs, right? So you could make 1.5 recipes worth, right? With the eggs, with the 3 eggs. You could make 2 recipes worth with the flour. So the limiting reactant is the eggs, or the limiting ingredient, right? You can make less recipes worth of with the eggs than you can of the flour. We're doing the exact same thing here, right? Just different numbers instead of recipes worth, it's moles. Um, but it's the same, it's actually the exact same idea. So we're going to see how many reactions we can do or how many recipes worth of the reaction we can do. Um, and we just use the coefficient here, right? And now notice how I'm not looking in terms of products here. I'm looking in terms of doing it once, right? So this doesn't, it's one recipe. I'm not telling you, how many products you're getting out of it, right? I'm not doing that right now. So for every one reaction, 1 mole of reaction, every time I do it, I need to use 3 moles of C6H12O, right? You'll notice that the moles cancel out, and then we're going to get some number here. 15 divided by 100.16 divided by 3. So this is why you divide by the coefficient before you see which one is limiting, because you're seeing which one does less reactions, right? That's what you're really doing by dividing by the coefficient. And if you don't, then you're making a mistake because right, just having more of something doesn't mean it's not limiting. Just like I said with the eggs and the flour, right? 3 eggs versus 2 cups of flour. When you need 2 eggs and 1 cup of flour, the eggs are still limiting, even though you have more. So this is the moles of reaction that you get from cyclohexanol. Now we're just going to do the exact same thing with the pure PCC. So I'm actually just going to skip a bunch of the talking just because it's the exact same thing. So you should kind of get the gist now. So for every 1 mole, we get 215.56 grams. Is there a question? I hear someone's mic is unmuted. And then we convert the moles into moles of reaction. So it's a 2 to 1. And then we just plug this in. We get 0.089. I'll go 4 decimals. 86. All right, so if you're looking at these two, right, which one makes less reactions? Which one does the reaction less times? It's this one, right? The cyclohexanol does the reaction less times. It's just a smaller number, right? Less recipes worth. So, and by the way, if you have a question, just feel free to chime in or say it in the chat because I'm just going to keep on continuing if you don't. I kind of won't wait like I do in discussion and ask if you have questions. I'm just going to keep going unless someone interrupts me. So now that we have the moles of reactions for each, right? Now you can do a few things with this. With this, you could figure out what is the theoretical yield of the product. So in this case, you're looking at this, right? You would essentially just multiply it by 3 to get the moles of cyclohexanone. And then, right, because you get 3 cyclohexanones for every one time you do the reaction. And then you can convert it to grams using molecular weight. That's it. So that's A, right? Where we're doing B here. And so how do you get the mass of the excess reactant, or how much excess reactant is left? What you can do here is first take a difference. So I'm going to take the bigger one minus the smaller, right? The excess one minus the limiting one. And then what does this do? So going back to the recipe analogy, I write this in, I'll say it. 3994. So going back to the baking analogy, right? If we did the eggs and flour again, let's use the same scenario. Again, 2 eggs one flour is one recipe. If you had 3 eggs, 2 cups of flour, then you can make 1.5 recipes worth with eggs, 2 recipes worth with flour, right? So what you do is if you take the difference between those, right, the bigger minus the smaller, so you know you have excess flour, you can make 2 recipes worth. You subtract it, you're left with zero point 0.5 recipes worth of flour, right? So you use the rest of it, right, to make the recipes with the eggs, but you're left with half a recipe's worth of flour left. And then you can just figure out how much flour that is, right? Because if you have half a recipe's worth of flour left, and you know every recipe calls for 1 cup of flour, that means you have half a cup of flour left, right? So just going backwards from that. But it's analogous and essentially the same. What does reaction represent? RXN is reaction. So just for this this whole thing happening, right? That's one reaction. Um, so this is telling us that we have about 0.04 moles of reaction that we, you know, worth of the excess reactant of PCC. So I have 0.04 moles of reaction left over from PCC. I can't use it because I ran out of cyclohexanol. Yep, cyclohexanol. And then we're just going to convert this back into PCC, right? So I know if I have zero point zero 0.04 recipes worth left over of PCC, I should make this more specific. This is PCC. We know that for every one reaction, we have 2 PCCs that we use, right? This big thing. And that's it. Let me get the moles. Or I guess it's not it. So that gives us the moles of PCC. And then we have to convert this into grams, right? So then we're just going to go ahead and multiply by the molar mass. No, not that one. By the molar mass over here, the 215 that we used before. So 215.56 grams of PCC for every 1 mole of PCC. And then we get 17.2, let's see, sig figs. So we have 4 sig figs as our limit, so we'll do 4 sig figs. 17.22 grams of PCC. And then that is the answer to part B. This is how you'll do basically all of any reactive problems. It'll always be like this. Find the moles of reaction of each. And there's a few ways you could do it, right? You could do how many moles of product do you get? And then you could see, which one is smaller, and then you need to figure out which one's limiting. I don't like that way just because it makes part B harder, right? If you have to find how much excess reactant is left, then you have to do like extra back calculation, or it's just conceptually harder, in my opinion, at least, to understand what's going on instead of just converting it into moles of reaction or recipes worth, and then converting it to, right, product or excess reactant. All right. So the next question I got was question 18 in the 2024. And then 2023 question 4. Okay, so I'll do it in that order. So question 18, 2024. I'm gonna erase this. And I'm gonna erase all of this. Let me just, yeah, I did pick the right one. Okay. So question 18 says a student weighs out 0.568 grams of KHP with that molar mass and titrates to the equivalence point with 36.78 milliliters of stock KOH solution. What is the concentration and molarity of the stock solution? Potassium hydrogen phthalate is an acid with 1 acidic proton. Okay. So I went over this one today with my class, but I know for those of you on Friday, I haven't. So what is a titration in general? Or I guess we should talk about the equivalence points. We didn't talk about that today either. So, oh, someone said something in chat. Um, okay, so order of questions, just for those of you that are wondering, I'm doing this one, then 2023 exam question 4, and then I'll go to 2024 question 4. So a titration in general is where you're adding an acid to a base. Now, if you're neutralizing the acid or the base, with one or the other, what this is telling you is that your moles of hydroxide are equivalent to the moles of H plus. Not the moles of the acid is equal to moles of the base, right? In particular, it's moles of H plus is equal to moles of hydroxide because not all acids only have one proton, not all bases have one hydroxide, right? They may be uneven amounts coming from each. So it's the moles of OH match the moles of H plus if you are neutralizing the solution or you're at the equivalence point. That's what that means for your sake right now. Um, doesn't really hold up in strong acids and strong bases, or with a weak base, or strong base with a weak acid, but it will hold up for strong acids and strong bases. So at the equivalence point, the moles of H plus are equal to the moles of OH minus. You have to know that. You just have to know that, otherwise you can't do this problem. So if you were to write out this equation, KHP plus KOH. Now, to be honest, I have no idea where the H comes from in the KHP. It doesn't really matter. We know that one H is going to come off. So I'll just write this as like K2P, right? And then plus water, right? The OH plus H, right? Gives you H2O. So I'm just assuming it's this hydrogen that comes off, right? But they tell us only one hydrogen comes off, which is important. So once we write the equation here, now what you can do is figure out the moles of, OH that you have in solution or the moles of hydrogen that you have in solution of H plus. Now, for the sake of this class, you assume that for strong acids, strong bases, you assume everything fully dissociates. At least right now, assume that. If you don't, it makes this a lot. I mean, I guess it doesn't make it that different, but it makes it different. So assume these fully dissociate. That's why I have a single-headed arrow here. Um, so we have the grams of KHP, and they tell us the milliliters of KOH, and they want the concentration of KOH. So if we need the moles of OH or of K or of H plus, we have to either figure out the moles of KOH or KHP because you can then figure out the moles of H plus or OH, right? Because they're in a 1-to-1 ratio. If it wasn't, right, then you could do a different one. If it was like strontium hydroxide, like from the worksheet, it's 2-to-1. So I'm going to go ahead and convert this KHP into moles. So 0.568 grams of KHP. And then we have 204 grams of KHP for every 1 mole of KHP. And now this is not moles of H plus, right? This is moles of KHP. I need the moles of H plus to know how many moles of OH minus there were because I know they're going to be equal, right? So we know that the KHP and H plus are in a 1-to-1 ratio. They tell us that KHP gives off 1 proton or 1 H plus. And then we plug this in and then let's get some number. I could kind of keep continuing with the conversions here, but I want to stop so we can talk about what's going on. 278, that's fine. Moles of H plus. Great. So we have this many moles of H plus. Now, as I said, we know that if you're at the equivalence point or you're neutralizing the solution, that means we have or use, right? I guess however we want to say it, 0.0270, oh, missed an O, 0.00278 moles of OH minus, right? These are the same as I said when you're doing these um, neutralization or equivalence point. So now that you know that you have this many moles of hydroxide, right, that you had to use in solution to get to the equivalence point, we can convert this into molarity of KOH. Right now it's pretty easy from here. Right, you should know that molarity is equal to moles over liters. And so they tell us the liters or the volume. We can convert that to liters, just divide by 1,000. And then that's it. Right now we want the molarity of KOH, not of OH. So I'm going to go ahead and convert this into moles of KOH first because we need moles of KOH for molarity. This isn't a 1-to-1 ratio, right? For every 1 KOH, you get 1 mole of hydroxide. Right now we're in moles of KOH. And then, oops, not equals. And then we go ahead and convert this into molarity by dividing by liters. So 1 over 0.03678 liters. And then we get a number and we're done. 0.0757 more. And that should be your answer. Except write KOH on that too. All right, anyone have any questions on this? Yeah, of course. So titration, H plus equals OH minus at the equivalence point. For strongness and strong base. All right. So next is, I think I said number 4 on this one. So no, 4 from 2023. Again, I'm just kind of going in order of these being asked. So for 2023. So number 4 says what multipliers are needed for the 3 respective simultaneous reduction reactions below in order to obtain this overall redox reaction. 3NO2 plus H2O plus 2HNO3 plus NO. Find the multipliers for the variables alpha, beta, and gamma. All right, so first thing to cover is what are the multipliers? So the multipliers are just a number that you're multiplying everything by, right? The coefficients by, so that when you add them up, you get what you want. That's really what it is. The other thing to cover is the negative. So what does the negative mean? The negative means that you're flipping it, that you flip the reaction. That's all it is. So the way you do this, I think the easiest way to do this is look at the products and the reactants and see what you need on each side. So things that we need on the reactant side are NO2 and H2O. And why is that helpful? Because if you look at these, well, the first one has an NO2. This one doesn't. The second one, the third one doesn't. So I know that the NO2 has to come from reaction 1, right? I know it has to come from reaction 1. It's the only reaction with NO2. So that makes this easy, right? If I want to get NO2 on the reactant side, so notice here it's, sorry, on the products, whoa, on the reactant side. Notice here it's on the product side. So if I want to switch the side, I know that alpha is going to be negative, right? Because I want this to go to the other side. I want it to be a reactant in my overall reaction, not a product. So it's going to be negative. And then 2 times what gives me 3? So the answer is 3 over 2, right? If you really want to do it, you could write out the algebra. 2 times what gives me 3? You get 3 over 2. And that's it. So alpha is negative 3 over 2. And we're just going to do the same thing for each of these. So let's see if there's another kind of unique reactant in here, right? Or if the other reactant is unique. So we did NO2, and that helped us get alpha. We can look at the H2O. There's no H2O in the first one. There's no H2O in the last one. There's only H2O here. So the water has to come from the second reaction. Now the coefficient is 2. This one is 1. So if I want to go from 2 to 1, then beta is going to be 1/2. I'm just going to have everything, right? Multiply all the coefficients by 1/2. And I don't have to flip it, right? Because the water's on the reactant side here, like it is in the net equation or the overall equation. Moving on to the right, we have 2HNO3. So let's see, which one has HNO3? So the first one doesn't, the last one doesn't, this one does, and it works itself out with this 1/2, right? Because you get 4 times 1/2, and then you get 2. So that's already done. And then what about this NO? So if we flip this first one, we end up getting, we'll check the other places where there's NO. Oh, there's 2. Okay, so I guess that's going to count too. So there's 2 reactions where there's NO. So if we flip this first one, right, because we're multiplying by negative 3 over 2, we have to get the NO2 on the right, on the correct side. So if we multiply it and flip it, we end up getting a 3NO2. So right now we have 3NO, or 3NO2, 3NO is what we have so far. All right, that's just from the first one, from multiplying by negative 3 over 2. But that's not right. You don't want 3NO. You want 1NO. So what do you do? So typically the way these work, these last reactions, usually you'll have 3 or 4. The last one, usually in the set of 3, is usually to cancel stuff out. That's just how it works. Because you'll notice if you were to write all these other ones, you have oxygens that show up that you don't have in here. Um, and you have a nitrogen, right, that doesn't show up in the overall reaction. So the last reaction is really just to cancel things out, right? That's all it's really for. So I notice that the NO is not the correct coefficient, right? I need to get rid of 2 of them. So how do you do that? Well, this is a 2, right? Well, if I want to get rid of 2 of them, then I need 2 on the reactant side because this is on the product side. I currently have 3 NOs on the product side. So I need 2 on the reactant side for everything to cancel out properly, right? Because then the 2 go away on the reactant side, and then you're left with 1 on the product side. So to get this onto the reactant side, I multiply this by a negative, and it's already the correct number. It's 2. So it's just -1. And then that's it. Um, it's going to be -1.5, 1/2, and -1. So the answer is D. That's how you do these. Just look at your reactants and products and kind of just go one at a time and then see which of them are unique, right? You can only get this one from this reaction and this other one and so on and so forth. Any questions? Because if you write out the whole thing and then you start to add them, it kind of gets confusing. It takes forever. It gets messy. Um, and this one, right, we didn't even have to look at the nitrogen or oxygen because it all sorted it out. Great, no problem. So the next one on the chopping block is question 4 on 2024 is what it was. Oh, okay. So question 4 is pretty much the same thing. So I will opt to skip this, but it's the same thing. Right, you just kind of look at this, determine where things need to go, right? So like boron is only in the first one, so you'd multiply this one by 1/2 to get it on the correct side. And then like this H2, it only shows up in the third one. So you multiply this by 3 over 2. Actually, no, I'll stick with this one because this one of the reactions don't work. So then for the B2H6, that one has to come from the second one. So that's negative 1/2, right? Because it has to go on the other side. And as a coefficient of 1/2. Now, this is almost done. So we have everything where we need them to be, but you actually run into a problem. So this is where the fourth one can be a little bit tricky. It's not that bad. I'm gonna go ahead and kind of, do I want to write? Oh wait, there's two. Oh no, no, that's good. Yeah, this is just not one. There's two ways you can do this from here. You can write them all out. Um, do I want to? Yeah, I mean, so there's one trick that you can do here. Again, I told you that in the third or fourth reaction, it's always to cancel stuff out, right? So if assuming you've done everything correctly, if this is just to cancel things out, you know you're only going to have to worry about water, the liquid and gas state. So you could basically just write just the waters from all of these equations to see how much you need to cancel out. Alternatively, you could opt to write like the whole thing, right? That's kind of the proper way to do it. And you could, check if everything cancels out. I promise you it does. Um, but that just takes a lot of extra effort and can take quite a while. So like do it here. But on a test, I wouldn't recommend doing this. 3/2 1/2 B2H6. And then 3/2 H2 plus 3 over 4O2. Um, oh wait, I wrote 3/2, but it should be 3/2 O2. Um, Yields 3/2 H2O liquid. And then what you would do here is you would really just like you would double check that everything kind of properly cancels. I'm not going to do it. I'm going to assume that my oxygens properly cancel. I know I did the math right. I'm assuming that these B2O, I mean, they do, right? It's 1/2 on both sides. Um, so that's fine. And the H we want. So the only thing left here that we don't want, so you can see the boron, we have the B2H6, and then we have the H2. The only thing that we don't want here is this H2O, right? Because it doesn't show up in the final reaction. So then what you do, and again, the shortcut would be just writing out the H2O parts, just so you don't have to write all of this. Um, but you can see this one has the liquid on the left, right? This one has the gas on the right. We have gas on the right or on the left. My bad. We have gas on the left on the reactant side. We have liquid on the right on the product side. And I want those to cancel out, right? So from this one, I want the gas on the reactant side. I want on the opposite side to make this go away. So I'm going to multiply this by 3/2, and it's already on the react or product side, so it will cancel out. And that's it. So whatever one matches this one. Um, this one, D, and then that's it. What concept to study? So I think it's just like multiplying reactions and then adding them. I don't think there's a um particular question. Is it a common question? I think it is. Yeah. Okay, great. So I'm gonna go and so kind of like what I said before, I think I said this in both discussions, but if you have trouble with algebra, make sure review it, get comfortable. Because I mean, stuff like this, right? It's not too hard. It's just a bunch of algebra. You have to be comfortable with it. So I did that one. So next is question 10 on 2023. Question 10 says, which of the following has the chemical formula C6H14? So this one, easiest way to do it, first count the carbons, right? You know that the ends and the vertices all are carbons. So this one has six, so that one's fine so far. This one has six, so B is fine. One, two, three, four, five, six, seven. So C doesn't work because you have seven. One, two, three, four, five, six. So, okay, so we've only eliminated C. So now what you have to do is count the hydrogens. So if you draw on all the hydrogens, remember the rules, each carbon has to have four bonds. So this one needs two more hydrogens. This one needs two more hydrogens. This one needs two hydrogens. This one has four bonds already. This one needs three. I'm not actually going to keep drawing the hydrogens. Just the red sticks are a hydrogen each. That one has three. So we count these up. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12. We're short a hydrogen. You do the same thing over here. This is 1 degree of onset. So we're going to end up with 14 again. Don't have to know that, but you count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or 12 again, I meant. But yeah, so B doesn't work because you have 12 hydrogens. For C, or C's eliminated, right? So by process of elimination, it's D, but if you were to count it, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And that's it. Okay. So that's question 10 in 2023. Number five on which one? 2024. Number five says an element has five stable isotopes. The percent abundance of each. So for number five, all you have to do is it's just a um what was it called again? It's a weighted average. That's what it is. It's just a weighted average. So all you end up doing, so if you want the formal formula, it's going to be the sum, that's the sigma symbol, the sum of the probability of some mass, which is the percent of the decimal, times the mass. So in this one, all you do is change the percents to decimals. So like 0.04, or whoops, oh 04. So we have 0.492 for 49.2% times 63.921. And then the sigma is just plus, right? You're just adding them all up. Plus 0.277 times 65.926 plus 66.921 times 0.04, not zero point 0.4. And I mixed the order up here, right? But it's multiplication, it's commutative, so it doesn't matter. And then we have 0.185 times 67.9248. And then we have 0.006, right? Because one is 0.01. No, yeah, 0.01. So you have to add another decimal here, another zero here, times 69.9253. And I don't really want to plug it in my calculator, but that's really it. Oh, wait, then ask which element. Okay, I'll go back then. I thought I was just going to ask what the average is. So what you do here is you first find the mass, the average atomic mass. Um, let's do parentheses here. 0.492, 63.92. Missed a 9 on my writing, but won't make a big difference. 277 times 65.976. 0.04 times 66.9271. Almost there, guys. One second. Syntax error. Okay, there we go. Thankfully, it was an easy one. So we have 65.39. And this is for your atomic mass. And then you would just look at your periodic table and see which one mass matches or most closely matches. I think this is copper. So copper is 65 or 63. No, so it's probably not. So it's probably zinc. Yeah, zinc is 65.38. So it's going to be zinc. And then that's it. Great. Uh, yep, of course. And then next, I see number 11 of 2023. Sure. I able to do a poll? Oh, I can. So I'm going to do a quick poll because you guys, what was this poll for? Um, sure. I'm going to launch a poll right now. So if you want, since you guys are, I mean, you're in your first year of college, if you want, I can give you some kind of general study tips, only if you want, right, want me to, because I don't want to waste your time. Probably take about 5, 10 minutes. I'll take a poll here. I'll take majority of a yes or a no. And it'll be after this question if it's a yes. Let me see, 11, 2023. That's surprising. Okay, so everyone said yes. That responded at least. Um, I guess everyone says yes. Okay, that's surprising. Okay, yeah, I'll do that. So we'll talk about it after um this one, number 11. So number 11 says, consider the following synthesis reaction with respective mole values. Sure. Sure. Okay. And it says, which is the limiting reagent? So this one, same thing, same idea as the first one we went over. So where we had where'd my thing go? There it is. Where we had moles of different things, right? And then we converted them to moles of reaction. You just do the same thing here. So we're going to figure out how many moles of reaction I can make with each of these reactants, right? How many recipes worth of reactions do I have, of Q and W and X and Y? So for Q, we just do 0.025. If you write it all out, moles of Q. If you wanted to keep the units, right? And then it would be for every 3 moles of Q, you have 1 mole of reaction. Um, that's not evenly divisible by 3. We get 0.00833 moles of reaction. So that's for Q. For W, we do the same thing. Mole W, mole reaction. For W, we use 5 moles of it for every 1 reaction. This one's 0.005 moles of reaction. And for X, I mean, so all these are going to be the same. Moles X, mole reaction, 2 moles of X, 0.0075. And then for Y, we do the same thing. 0.025 moles of Y, 4 moles of Y, 1 mole of reaction. 0.00625. And then we just look at which one is the smallest, right? So you can see here, so just comparing the first two, that W is smaller than Q. And then W is smaller than X. So we're still at W. And W is smaller than Y. So W is the limiting reactant. And that's it. You can make the least, do the reaction the least amount of times. Least recipes worth. Okay. So any other questions on this one? Great. Um, okay, so we talk about general study tips. I won't write anything here, but some general study tips for I think just college in general is a few things to keep in mind. So first thing is, and like I know it's easier to hear than it is to um, experience. It's easier to say than experience, but your grade doesn't really define you. So if you don't do well on the first midterm, that's okay. It happens, right? If you don't do well in the whole class, that's okay. It happens, right? But what you do next is what matters more, right? And so if you don't do well, make sure you analyze your mistakes, right? Analyze what you could have done better and then do those things. Um, don't don't let, um, it ruin your whole self-esteem and self-worth and stuff. It's just a test at the end of the day. And so speaking of that, tests are tests, right? Tests don't test your knowledge. They do, but they test your knowledge under a time constraint. So some of you are really good at solving problems given enough time, but you don't have all the time in the world, right? You're given like 50 minutes or something for the test. And so in general, just remember tests are done under a time constraint. So when you're doing practice problems and you're studying for a test, right? This is specificity. You're studying for a test. You should study under a time limit. This is something that significantly helped me in undergrad. Um, is probably by far, I think that the thing that helped me the most, or scoring really well the most. So if you test yourself under a time constraint, there's a few things that happens. When I say that, that means like take one of these practice tests, do it in the time that you would an actual test, right? Study the material. You should, and studying shouldn't take you too long, right? If you've been caught up with content, it should probably take you maybe like 2, 3 hours at most, right? To kind of review and catch up, just kind of redo things. And again, I'm not saying know everything, right? But you should have a decent grasp, right, by the time test day comes, or by the time you're doing these practice exams. And so when you have a decent grasp, you should give yourself the same amount of time that you would on the actual test. So if you're given an hour and a half, you do an hour and a half on this test. No more than that. Right now, the reason why is you need the time pressure because a lot of people, especially when you start out college, even later on, honestly, in your upper div classes, people just sit there. Like people just sit there and you're not sure what to do. And you keep sitting there and you keep doing nothing. And, a few things that could happen is like you could have just gone ahead and done other problems and figured those out, got more points. Um, right. But don't, or yeah, and so then you run out of time. Um, but there's a few like and other things that you learn from working under a time constraint is you also just learn to pull from somewhere or just to try things. And this is generally true for those of you that do that if you do want to do a PhD or a master's and you do research, this will be true. For doing engineering. I mean, in a lot of places, this is just generally true. You just try it, right? You just try things and you see if they work. And so if you're under a time constraint, right, you have more incentive to just try something and see if it works or doesn't than to just sit there. Because a lot of you, myself included, right? Even I'm still guilty now sometimes when it comes to projects, but you just sit there and you do nothing. And I like it's good to think through the problem. It's good to think about what they're telling you. But I think a lot of people waste a lot of time trying to figure out how to entirely solve the problem instead of just trying something, right? You often will not have the answer in your head from start to finish if you're not experienced in the material, right? You just won't have the answer from point A to point Z, right? It's just not super common unless you've done a lot of the same problem. And so when you're doing these tests and when you're practicing, you should just try something and see if it works, right? See if you can get the right answer. Because when it does work and you're practicing, it's going to stick with you. And on an actual test, you will learn to know what doesn't work and what does work. You're going to try something and you'll be like, this doesn't give me what I need. I need to try something else, right? And you just move on, right? Instead of just sitting there and being like, I'm not sure what to do. And you kind of just sit there and do nothing, right? So time constraint, practicing under time constraints is important when you're comfortable with it. So usually 2 or 3 practice tests is fine per midterm. Um, I mean, I used to do one, but like 2 is usually enough, right? If you're, again, already comfortable with the material. On the second or third practice test, you could like have your time or give yourself 3/4 of the time that you normally would. And then this again just trains the same thing. It just trains you to think on your feet better, trains you to just try things, right? Just try things and see if it works. Um, and that's it. Because I think the other problem with like not working under a time constraint is you kind of let your brain wander. I know a lot of people that are guilty of that. Like sometimes you're thinking of the problem, you don't know how to do it, but a lot of people also just sit there because you think you have more time than you actually have. Right? You're kind of there, you're like, oh, I'm not sure. You're like, it's okay, I got 5 minutes, like maybe just take a second, and then all of a sudden, you lose a bunch of time. So that's my biggest tip is work under a time constraint. Study early. This is coming from someone that even still guilty now that is a really bad procrastinator. Just study early, just get your stuff done early. And even though things turned out fine for me, I would have built a lot better habits and I would have had a much less stressful time come midterms if I had just done things earlier and done them on time, right? Because the amount of time is still going to be the same that you spend studying. You're gonna if you need to study 10 hours, it's 10 hours, whether it's in one day or spread throughout the week. It's the same, right? Same time commitment. One just makes you miserable, the other not so much. So study early, study consistently. You should set up a schedule for yourself to study. And then you should also like schedule, time for yourself to do things, right? Don't study all day, but like give yourself a break where you can do different things different for different people. Like some people like the Pomodoro effect or Pomodoro technique, sorry, where you like study for 20 minutes and then take a 5-minute break. Feels too short to me. Some people do like triple that. So you study for an hour, take a 15-minute break. That's like closer to what I do. But or 40 minutes and 10 minutes, right? But find something that works for you and set up a consistent schedule. If you're consistent, it'll make your life easy. I promise. This is true. Just in general. If you are a consistent person, you will make your life significantly easier than if you are kind of putting band-aids on things and doing it last minute. Going for studying, going for research. And so when I talked about research before, right, you just have to try things. That's often how it is, right? You try to figure out a solid way to start something, but you just got to try things. But you just need to be consistent. And if you're consistent, like 95+% of the time, things will work out. They'll work out for the better. You'll make your life a lot easier. Um, right? Because at the end of the day, if you're also consistent, you did your best, right? You planned for everything, that you tried. You can reevaluate things and do it differently. There's nothing wrong with that. But you did your best and that's something you should be proud of. So those are my study tips. Anyone have any questions on those? And just general life tips. Yeah, just don't procrastinate. That's like the worst thing you could do coming from a procrastinator. Oh, someone asked, sorry, so this was about the question. It says, why is it moles of reaction instead of moles of Z? So there's two ways you could do it for the a number 11. You could do it in terms of moles of product, right? Like how much product do I form and which one gives me the least? I don't like doing it like that because of finding the excess reactant part. So instead, what I do is moles of reaction, right? How many times do I get to do this reaction just in general? And I think that's just it just makes some problems a lot easier and it makes it conceptually easier to kind of bridge the gap between certain units. But either way works. You could have done moles of Z, but you would have to just do a two, make sure you get the stoichiometry right. You would do like 2 to 3 or 2 to 5, right? And so on and so forth. Okay, because so no one has asked any other questions regarding the exam at least. Um, yeah, I think that's it for study tips. I really think that's it. And just general college tips. Yeah, just get your stuff done. Don't wait. Don't be like me. It's it's not worth it. It's not worth it. Um, yeah, don't do that. So there's another thing that I could think about doing because I was thinking about doing this until 9. I don't know how long you guys are gonna stick around. Would you guys like me to go over redox? Because redox is actually really easy if you know the way to do it. Whoa, that was fast. Um, said redox, and then I got eight replies. Okay, so we'll do redox. Not that one. Where's the redox one? Let's see. So redox feels pretty hard the first time you do it. And to be honest, I honestly is one of those things that I kind of just didn't really learn until grad school when I had to go back and then learn how to teach it. But it's really easy. It's actually really easy if you know what to do. I never knew what to do. There's always different rules. I'm going to make this very easy. I'm going to give you rules that you will always follow and it will always work. Um, do I like this one? Yeah. Yeah, I like this one. This is a redox, right? Yeah, it is. So why don't we do number 20? This is a redox problem. So why don't we talk about terminology first? What does it mean for something to be oxidized? Something's on top right. So for something to be oxidized, what it means is that actually I don't like that. Let's start with reduced. Reduced is easier. So what does it mean for something to be reduced? So when something is reduced, it's a reduction in charge. That's all it is. It's a reduction in charge, which means you gain electrons, right? So you go down in number, right? In charge, you gain electrons because electrons are negative. You're adding negative charge, right? Which is a reduction in charge. Not in magnitude, but in number. So reduced is a reduction in charge. You're gaining electrons. And then oxidation is the opposite. It's an increase in charge. So I went over reduction first because that one's easier. And then oxidation is just the opposite. There's no really easy way to remember this. In OChem, it's like generally increasing bonds to oxygen, but again, it's not going to make sense. So reduction is reduction in charge or gaining electrons. Oxidation is increasing in charge or losing electrons. That's it. So if I'm asking you what element is oxidized, I'm asking you what element goes up in charge. If I ask you what element is reduced, I'm saying which element goes down in charge. Now, here's a question for you guys. Did Dr. Farahat cover oops, oxidizing agent. Was it oxidizing agent and then reducing agent? Okay, so I don't see anything in the chat, so I'm going to assume no. Oh, I see one. Yes. Okay. So if he did, so a reducing agent is the thing that does the reducing, right? So if you're reducing something else, I'm giving an electron away. That's what it means. It's the thing that gives the electron away. Then it's being oxidized, right? It's reducing the other thing, but it's the one being oxidized. If it's an oxidizing agent, that means that it's taking an electron or it's being reduced. So reducing agents are oxidized, oxidation, oxidizing agents are reduced. Um, they're opposites again because it's doing the thing to the other one. So if something's reduced, again, just to recap, gain electrons, oxidation, you lose. And then the agents are based off of that. All right, so now we can actually talk about how you do this. So I'm actually going to get some space on the left here. I'll wipe this out. And we're going to do a list. So here is our kind of order for balancing our redox. So step one, identify what is oxidized and reduced. Right, so how do you do that? You just look at the oxidation states. So in the first discussion, or second, I don't remember which, first or second, we went over oxidation states. You're just doing that, right? You're seeing what goes up in charge and what goes down. So easy ones are usually elements. So you can see this Hg here goes into Hg plus one because there's two of them, right? So it's a plus two overall, and there's two, you divide it by two, it's a plus one. So Hg goes into Hg plus, right? So that means that Hg is oxidized. It goes up in charge. I'm not going to write the whole word. Hg is oxidized. Then you can figure out what is the other one. So notice here, you're like, well, is it oxygen or is it hydrogen? Well, that's not hydrogen, that's Hg. Or is it hydrogen? The only thing in common here is the sulfur. Right? Again, kind of think of it in the what we talked about in class, right? Some things have a typical oxidation state. So usually oxygen is -2, usually hydrogen is +1. And we're going to just assume that's true for both of these, right? So sulfur is the only one left that can change or vary. So if you look at this, you can see that sulfur has an oxidation state here of 6 plus. Yeah, why do we always put the plus after? I don't know. But it has a oxidation state of 6 plus, right? Because the oxygens add up to -8, each -2. We assume that times 4, -8, plus 6 to get a -2. And then the sulfur over here is a -2 or 2 minus, right? Because the hydrogen is a +1. We assume that that's generally right. And then you have an overall minus sign. So to go from +1 to -2, you add -2. So that's it. So sulfur goes from a +6. And you don't have to write this. I usually don't. I just kind of want to make it more clear here. But you can see it goes from a +6 to a +2. So we know that sulfur is reduced. Great. Why is this important? You technically don't have to do this, but it's going to matter in a second because it'll help you check your electrons, which everybody seems to like to mess up. So two, then what we're going to do is write the half reactions. We're going to write and balance the half reactions, right? So these are the oxidation or reduction. Oh, I messed up the order. The oxidation or reduction half reactions. Doesn't really matter what order, you just have to do both. But they're both two halves of a whole, right? One is oxidized, one is reduced. Together they do redox. So how do you do this? Well, the first thing you're going to do is I'm going to start with a reactant. I'm going to leave some space here. And then I'm going to write the product that it turns into. There we go. So I'll start with the Hg. I'll just write it on the left here. That's fine. That's good. Okay, so, and then I'll write the sulfur right now too. Why not? This is too high. I'm going to run out of space. So for the sulfur, we have SO4, the reactant. Again, this was just to kind of identify the charge. I usually don't write this in. 2 minus, but we're writing the reactant here. I'm going to leave some space, and then we get HS minus. All right. So I have the reactants and the products. Now what do you do? So step one of step two. Maybe I'll write an I here. So step one of balancing these is you balance the non-hydrogen and oxygen atoms. So you just balance them like normal. So I'm going to do mercury's well, mercury, I guess, is done after the first step. So let's just do mercury first. Right? I need two mercuries, two Hgs on the left because I have two on the right. For sulfur, the sulfur is already balanced, so we don't need to, right? There's one on each side. If it wasn't, then you would just balance them using numbers. So that's step one. Then step two. So we're going to go to sulfur for this because the He is basically done until the end. Um, for step two, we're going to go ahead and balance the oxygen using water. So on the left, there's no oxygen, so you don't have to balance it. On the right, though, right, we have four oxygens here. I need four oxygens on the product side because of conservation of mass. So I'm going to add four waters. So I have four oxygens. Then once you do that, step three is to balance the H plus or what balance the H, sorry, not H plus, balance the hydrogens using H plus. There we go. So on the left with mercury, there's no hydrogens. That's Hg bundled up. And then we have on the right, for sulfur, there are hydrogens on the product side, right? In the reduction half reaction here so far. I have 9 hydrogens. So I need 9 hydrogens on the left. That's it. So again, once you do like 2, 3 of these problems, it's always the same thing. You just follow the chart, memorize it if you have to. You'll see this come up again in 2C, but you'll always do the same thing every single time. It'll always be these. So you balance the hydrogen using H plus, and then step 4 is you balance the charge using electrons. So for mercury, right, if I want to balance the charge, you can see we have a 2 plus here, right? And it's neutral over here. So how do we balance the charge? Well, an electron has a charge of -1, right? So what I'm going to do is add two electrons on the right because I have 2 plus over here, +2. Over here, I have no charge, right? It's neutral. And to make these the same, I need -2, right? Or I need 2 electrons. So balancing the charge using electrons. So this mercury is actually all balanced. That's done. Um, and then for the sulfur, we're just going to do the same thing, same exact thing. So we get, let's see, on the left here, this is a -2 from the sulfate. Then we have 9, and then we have a -1. So if we add these up, what that's -7, that's +7 equals -1. So I need to bring the charge on the left down by 8. So I need to add 8 electrons here, right, to get to -1. So I can add the 8 electrons here, and then this should be balanced. It is. Great. And then that's done. So the charge is now balanced. So now you've basically done the hardest part at this point. You balance the half reactions. Anyone have a question so far? Okay, I don't see anything. So it's balanced now. The half reactions are balanced. Again, you will follow this every single time. Teachers may teach it differently. Honestly, just do it the way I'm doing it, so that way you don't get confused. Sometimes for basic solution, they'll change it at step 3. Honestly, don't do it. Just, yeah, just do what I'm doing here until the very end. There's a caveat. If your teacher asks you to do the half reaction in basic solution, then I guess you have to do it their way. That's kind of annoying. Um, but usually they don't. Usually they ask you to just get the overall reaction in basic or in acidic solution. So just follow this. It should work for like 99% of your problems. Um, yeah. And sometimes again, they just do what I will do at the last step at this step 3. Um, I put a note here. Sometimes um, teachers do here. And I'll talk about what they do there, right? It'll kind of be an arrow that comes back up. So now what do you do now? So step 3, because these are balanced, is you're going to multiply. And actually, before we even talk about step 3, right, how do you check if this is right? So this is from step 1. We said that mercury is oxidized, right? That means that mercury is giving away electrons, which means the electrons have to be on the product side. They have to be on the product side. Don't make this mistake on your test. See it all the time. Um, if it's an oxidation reaction, electrons have to be on the product side. They have to be. Otherwise, it's not an oxidation reaction. And if it's a reduction reaction, the electrons have to be on the reactant side because they're receiving electrons. They're going down in charge. If it's not on the reactant side, it's not a reduction reaction. So please be careful. Please don't make this mistake on your test. I see this all the time. Reduction, electrons are on the left, on the reactant side. Oxidation, they're on the right. They're a product, right? They're given away. So now step 3 is we're going to multiply the reactions such that the electrons cancel out when added. So really what you're doing here, right? Really what you're doing is you're using the least common multiple. So the least common multiple of 2 and 8, right? The electrons from both of these reactions is 8, right? 2 goes into 8. If it was like 3 and 4, that would be 12, right? So you'd multiply them to be 12. But in this case, it's 8. So I'm gonna multiply the first reaction by 4. Where am I gonna do this? We'll do it over here. To get 8 electrons. So this is gonna be 8 Hg. That's a 4. That's an 8. And then for this SO4 one, I'm just gonna multiply it by 1, right? Or do nothing, basically. And then I'm gonna add these up. I want these closer. I don't like that. Oh, I should have just kept it. I'm gonna just move the arrows over in a sec. Because it looks like the 8 electrons are in the same spot, but they're not. It's just because the arrows aren't lined up. There. Oh, that's kind of ugly. Let's just move it the other way. Sorry, I'm being picky here. All right, there we go. So now I'm adding up these reactions, right? You can see the electrons cancel, right? As desired. Why did I multiply by 4? I multiply by 4 because we want the electrons to cancel, right? So if I multiply this by 4, this is going to be 8, and I have 8 electrons here. You're using the least common multiple of the two electron coefficients is what it is. So the least common multiple of 2 and 8 is 8, right? So I need to multiply this one by 4 to get 8, and this one is just 1 to get 8. If it was 3 and 5, the least common multiple is 15. So the one with the 3 electrons would be multiplied by 5. The other one would be multiplied by 3. So now we can add these up. You see the electrons cancel, and then everything else doesn't. So then we get SO4, 2 minus, and then I'm just going to say 4 is add the reactions. So we get SO4, 2 minus, plus 9H plus, plus, no, the electrons went away, so that's it. We get Hg, no, what am I doing? 4 Hg, 2 plus, plus Hs minus, plus 4 H2O. Now, if you're in acidic solution, this is done. So if they ask you to balance it in acidic solution, this is done. Right, this would be your answer. Now, in this case, they're asking for it in basic solution. So there's one more step you do, or I guess it's 2, but it's like 1 and then a simplification. So again, this is done in acidic. And then this is for basic solutions. So in basic solutions, the next step here is you're going to add the same number of hydroxides as there are H plus to each side. So also I want to note, sometimes you're going to get like H's on both sides here. Make sure you cancel them when you're adding them, right? But you should be, when you're adding them, you should reduce it down all the way. And then that's it. Where did the 8 Hg go? Oh, thank you. Yeah, I just dropped it. I totally missed it. Thank you. Good catch. So for the basic solution, all we're going to do is add the same amount of hydroxides as we have H plus on each side. The reason why is because keep in mind that hydroxide plus H plus gives you water, and then things are just going to cancel out, and that's it. And then I guess step 6 is just cancel stuff. or you could even write as like 5 part 2. So in basic solution, we would add 9 OHs to each side because we have 9 hydrogens here. The OHs don't do anything on the right? So we're just going to write them separately. And then we get 8. I really don't want to write this all, so can I copy this? No, I can't. Okay, I guess I have to. So we get 8Hg plus SO4 2 minus. These turn to water. 4Hg two plus HS minus 4H2O 9OH minus. Great. So that's the whole thing, right? And then you just cancel. You just cancel the waters, right? So that turns to a 5, and then you would rewrite the whole thing. Or 8Hg SO4 2 minus 5H2O. So it's just more tedious at the end with the base. Um, plus HS minus plus 9OH. And then that's your answer. That's your answer in basic solution. Now, the step that's usually done, not usually, sorry, that's sometimes done depending on your teacher in step 2, part 3 is step 5. This is the one that is sometimes done to both half reactions where they balance it with H and then they add OH to both sides. Um, I don't do that just because it's a little more tedious doing it my way because you have more stuff to write at the end. Well, is it? I mean, I guess overall it's the same. Never mind. So I guess technically it's about the same in speed, but I just do it at the end because it makes it really streamlined, right? You just do it one way, and then if you need it, you just add something on instead of doing it in the middle. It's easier to remember it at the end. How did I get the 5? Because there were 4 waters on the right on the product side, and there were 9 on the left, so you can just cancel them out. So you do the 9 minus 4. We'll give you this 5. And then that's it. So this is redox. If you have this written down and you memorize it, there's like ways they can make it trickier, like the same thing is oxidized and reduced. I've seen a teacher do that, but ultimately it's the same thing, right? Once you recognize that, it's just the same thing is oxidized, the same thing is reduced, and then you write the half reactions, and then it's exactly the same. So they're always like this. So if you can remember this just in this order, again, just maybe get flashcards, spend like an hour, half an hour. I don't think it take too long. Do 1 or 2 or 3 problems, and you're done. You will always get these right if you know how to do this. Um, yeah. And you can see they're very mechanical, right? If I can write out an exact procedure, it's very mechanical. Right? It's always the same way. Any questions on this? Okay. So that's the whole redox kind of stuff, redox, I guess, lecture that I didn't do in discussion. So that way the people on Friday can also see this before the test. But yeah, that's really it. I can't think of anything more general for the test. Um, Anyone have any other questions before I end this? Because I don't see any other test questions queued up. Okay. What do you recommend we study the most? So I don't think there's ever really study the most, to be honest. Just because all of it's so intertwined, right? If you had to pick, right, I mean you should know the conversions. Um, you you need to know conversions. You need to know how to manipulate formulas and do algebra with them. You need to know limiting reactant stuff because that stuff will come up forever. Um, right? And it's just in different forms because I think a lot of it is just you keep building from the foundation. So if you had to choose, I would pick those foundational things, right? Know the algebra, know conversions, understand conversions, and just the ideas, like why you're doing things. It makes it easy, a lot easier to remember it. And yeah, just because again, they all come up, right? Titrations are just a conversion problem, really, right? At the end of the day, it's just equimolar amounts and it's a conversion problem. And that's it. Conversion from one to another. If it's not, then it's a limiting reactant problem, right? At the end of the day. Redox is kind of its own thing, right? So this one is like, one of the free response questions usually that you just know it or you don't. But yeah, the other foundational things just come up all the time, right? Because they're just variations of the same thing. So be very comfortable with the algebra and conversions and stoichiometry and stuff. Any other questions? All right. So I guess if there's no other questions, I'm gonna stop the recording here.